So, based on the values of the way I have explained, the random variable or the stochastic process is going to be x of w comma t, where w is belonging to omega and t is belonging to capital T. There are two approaches can define the stochastic process. The first one, that is we name it as a case 1. I can say it as the collection of random variable as a family of random variables as a x dot t, where t is belonging to capital T. So, this is the way I can create the random variable, and this is the easier approach, in the sense, once I know the different t, for fixed t it is going to be a one random variable, and I have collected a family of random variable for different values of small t. Therefore, this is the way we can create the stochastic process, and this is the easier approach also. The next one, that is a case 2, that is nothing but as a set of functions on capital T, that is nothing but a collection of x w comma for w is belonging to omega. That means I have made a function on capital T, and once I fix one w, I will have a one function, and if I fix another w, where w is nothing but a possible outcomes. Therefore, if I have a different possible outcome, that is going to be create a different stochastic process. Therefore, I can create a stochastic process of x of w comma t, either fixing a t or fixing the w. Accordingly, I can have a two different ways of creating a stochastic process. And the case 2, the way I have made a collection of random variable by fixing the w, then I made a functions on t. Therefore, this is going to be the method of realization of the process, or it is going to be called it as a trajectory, or it can be called it as a sample path, or it can be called it as a sample function also. So, these are all the different ways the case 2 can be called. That means, once you know the one possible outcomes, therefore, you are tracing the stochastic process along the one possible outcomes. Therefore, that is going to be called it as a realization of the process, or a trajectory, or the sample path. So, the conclusion is you can always define a stochastic process as a collection of a random variable for different value of a t, or you can go for a collection of functions on t for a different values of the possible values of possible outcomes, that is a w belonging to omega. So, these are all the two approaches can create the stochastic process. Not only we can go for making a one dimensional random variable or one dimensional stochastic process. So, you can create a stochastic process. It could be a one dimensional, or it could be a two dimensional, or it could be a n dimensional also. So, first we have discussed what is stochastic process and how to create the stochastic process, whether it exists and so on. Then we have given the parameter space and the state space. Then we have given what are all the ways we can create the two different approaches you can create the stochastic process. Now, we are discussing what is the dimension of the stochastic process. So, either the default it could be a one dimensional, or it could be a two dimensional, or it could be a n dimensional. Let me give a one simple example in which it is going to be a two dimensional. That means, I have a random variable x of t, that is going to be a x1 of t comma x2 of t, in which x1 of t is nothing but the maximum temperature and x2 of t could be minimum temperature. The maximum and minimum temperature possible of a place at any time t, and this together is going to be a one random variable. That means this is a random vector which consists of two random variables x1 of t and x2 of t. That means for fixed t you have a one random vector x of t, and therefore you have a random vector for over the t, and this random vector will form a stochastic process. Therefore, this is going to be a two-dimensional stochastic process. Therefore, in general you can define a n-dimensional stochastic process with for every t you have a random vector x of t, that is going to be a x1 of t comma x2 of t and so on. It is going to be the nth element is xn of t, that is going to be a n tuple in which each one is going to be a random variable for fixed t, and this is going to be a random vector for fixed t, and this is going to be a n-dimensional stochastic process in which each one is going to be a one-dimensional random variable for fixed t. That means you can go for making a one-dimensional random variable, then you have a collection of random variable from a one-dimensional stochastic process, or you can have a two-dimensional, like that you can have a n-dimensional stochastic process. In the course what we are going to discuss always it's a one-dimensional stochastic process. We can always create a complex valued stochastic process also in the form of x of t. Let me define it here. The x of t is going to be x1 of t plus I times x2 of t, where I is nothing but the complex quantity square root of minus 1. That means the x1 of t is a real valued random variable for fixed t, and x2 of t is also a real valued random variable for fixed t. The way I have made it the x of t, this is going to be a complex valued random variable for fixed t. Therefore, the x of t over the t, that is going to be form a complex valued stochastic process, because for fixed t x of t is going to be a complex valued random variable. The corresponding stochastic process is called a complex valued stochastic process in the one-dimensional form. Like that you can go for the multi-dimensional complex valued stochastic process also, but in this course what we are discussing only the real valued one-dimensional random variable most of the times. Sometimes we are discussing real valued two-dimensional or n-dimensional stochastic process, that too with the real valued random variable, not the complex valued. So, now we are going for classification of a stochastic process. The way I have explained the parameter space capital T, the capital T is a parameter space and capital S is going to be the state space. That is nothing but the collection of possible values of x of t and the possible values of a small t belonging to capital T, that form a parameter space. Some books they use the notation parameter set also, and the capital S is going to be the state space. Now, based on this we are going to classify the stochastic process. Suppose let us start with the capital S. Suppose the possible values of S, and what is the name of the stochastic process if S is going to take the only countably infinite or countably finite values, then it is going to be called it as the corresponding stochastic process is going to be called it as a integer valued stochastic process, or we can call it as a discrete state stochastic process. So whenever the possible values of S is going to be a countably finite or countably infinite, then we say it is a integer valued stochastic process or a discrete state stochastic process. Suppose the possible values of S is going to be the real values, then we call it as a real valued stochastic process. Suppose if it takes a Euclidean space with the k dimensional Euclidean k dimensional space, then we call it as a k vector space, k vector stochastic process. That means the each random variable going to have a one dimensional random variable, and like that you have a k random variables for fixed t. Therefore you have a k vector stochastic process. Therefore it is going to be called it as a k vector stochastic process, in which each element is going to be a one dimensional random variable for fixed t. So the collection that the k tuple values stochastic process is going to be called it as a k vector stochastic process. Similarly, you can go for, based on the capital T, what is the name of the stochastic process for different values of t. That means if it is going to take the value countably finite or countably infinite, or it is going to take only the integers values, then we say it is a discrete parameter stochastic process, or we can, there is another name, it is called the stochastic sequence also. Whenever the possible values of a capital T is going to be a countably finite or countably infinite, then we call the corresponding stochastic process as the stochastic sequence, or it is a discrete parameter stochastic process. Otherwise, if it takes a uncountably many values in the capital T, then it is going to be called it as a continuous parameter, and it is going to be called it as a stochastic process itself. Therefore, based on the discretize, it uses the word sequence, or if it is going to be a uncountably many values of capital T, then it is going to be called it as a stochastic process. So based on the classification, I can go for making a one table in which the possible values of S will take a column and the possible values of capital T will take a row. So either it could be a countably finite or countably infinite, that I uses the word discrete. If the possible values of t is going to be uncountably many, either it is set of all intervals, or it will be a whole real line itself, or it is going to be a union of many intervals. In that case, it is going to be called it as a continuous parameter. Similarly, if the possible values of S is going to be a countably finite or countably infinite, then the state space is going to be called it as a discrete. Similarly, if it is going to be uncountably many values, then it is going to be called it as a continuous. So accordingly, you can classify the stochastic process into the four type, in which if the t is going to be a discrete as well as S is going to be a discrete, then it is going to be a discrete time. Discrete time or discrete parameter, both are one and the same. So discrete time, discrete state stochastic process. Similarly, if the t is a discrete and the state space is continuous, then we can call it as a discrete time continuous state stochastic process. Similarly, this is going to be a continuous time discrete state stochastic process, and this is going to be a continuous time continuous time, continuous state stochastic process. That means based on the possible values of a capital T and the possible values of capital S, any stochastic process can be classified into the 4 types, in which it is going to be a discrete or continuous or discrete continuous based on the time and the state space.